Thank you guys. And thank you guys for showing up. 8:30 in the morning on a Saturday is a tough one. So I guess this topic was compelling enough for you guys to come in and join. So hopefully I can impart some knowledge on you, or you walk away with some information. So Mo already spoke a little bit about myself, so I won't go too much about this. Again, I've been a dental technician since 2006. My dad kind of just hauled me out of bed one day and said, hey, you're not doing anything with your life, so you're going to come to the lab and do something productive. And here I am, almost 20 years later, lecturing in front of you guys. So it's wonderful. Casper, thank you as well, and the whole ELOS team for the invitation. It's always wonderful to speak about digital dental technology and things that I'm so passionate about. So the title, again, for today is Precision and Progress, Rethinking Tie Bases in Modern Full Arch Restorations. So just to kind of gauge the competency level of the whole room, who here is working with full arch, all on X? Okay, pretty good. Who here is looking to get into learning how to do all on X? Okay, all right, good. Okay, so why does this topic matter, right? Why do we need to rethink tie bases? Why are screw-only systems kind of the hot topic right now? Why is full arch such a hot topic and trend? What I've noticed in recent years is there's a real big shift in full arch restorations where a lot of people are adopting screw-only systems. Everyone's kind of familiar what I'm referring to when I say screw-only systems, so I don't have to name any names. And then, of course, titanium base systems, right? So titanium bases are the conventional ones where you have to lute a pre-manufactured titanium base into a full arch. So the big thing, and it's always very important, is to focus on passivity. So we're going to speak a little about passivity, stability, and what that is and how we kind of gauge passivity. And then finally, understanding some of the engineering limitations and how they really impact, ultimately, the patient that these things are going into. So, of course, the rise of screw-only systems is because there's a need, there's a demand, there's obviously a great trend for it. And it eliminates the need for tie bases, right? And the big thing is it reduces cost. Titanium bases aren't cheap. You order 6, 8, 12 if you're doing double arch. The costs add up. And there's complexity. Who here personally cements tie bases in their lab? Do you like doing it? You got to block out the screw holes, maybe Teflon tape, maybe wax. If you get a little bit of in there, then you got to go in with like a diamond burr to clean it up, and it just gets messy, right? So it's not an enjoyable process. There is some downsides to it as well. If your cementation is not perfectly right, or you're just trying, I'm going to do 6 in 1 because I'm really rushed, right? And then the cement kind of sets up a little bit faster. You got to debond everything. It's a pain, but the components themselves are very, very important. We'll kind of cover why in a little bit later. The other reason is because it overcomes machining limitations, right? So most mills that we have, most mills have like either a 2.5 round burr, a 1 millimeter burr, and maybe like a 0.5, but they're all round burrs. If you go to like a more like robust mill, you'll have something that has a flat end mill that'll be able to mill screw seats. So the designs on these screws also have a taper to them, which make them a little bit easier to machine. And of course, the marketing, you have they're very good at marketing to clinicians and kind of upping the demand for them. So we'll kind of cover some common failures and challenges as well when we go a little bit deeper into this. But screw loosening, who here is clinician? Clinician, okay. Labs, everybody else. So if you're working with these systems, who is working with screw-only systems? Okay, have you guys experienced any screw loosening, any breakage of screws, anything like that? Yeah, got a little bit of screw loosening. Okay, I'll talk to you a little bit about that as well. Why these potential stresses, these excessive forces are not ideal. And then, of course, why this ultimately leads to implant loss or implant failure, right? But of course, we're getting a little bit ahead of ourselves. I always like to kind of start with a foundation, like a foundational knowledge on implants, right? And this is what I call the levels of implants. So a very quick, brief history of implants. And really, the first foundational principle is osseointegration. This is the whole foundation of implant dentistry. And it was really a happy little accident. Osseointegration is the process of bone fusing to a foreign object, typically titanium. It will fuse to other implant materials, but typically it's a titanium implant. And it was discovered by accident by Professor Brennemark. And he was working on, I believe, like a rabbit's foot or leg or something like that, and he put a piece of titanium in there, left for the weekend, came back, and he noticed that it was fused together with it. And he was kind of presenting this for many years, and it wasn't really generally accepted for quite a while. But as you can see now, implant dentistry is a multi-billion-dollar industry, and a lot of us rely on it for our livelihoods. So of course, this osseointegration accident is really the basis of all implant dentistry. The next level that I speak about is the actual designs of the implants, right? So a lot of happy accidents, but we've learned over the years that varying styles of implants are better for certain situations. The first implants, the Brandemark implant or the external hex, was really just a flat seat with an external hex that you could seat on. You could visually see everything. But what they noticed over time was there was lateral movement, right? And that lateral movement would cause crestal bone loss and other things, micro movement. So over time, they learned that engineering a Morse taper, this here, would wedge this implant into, well, the prosthetic into the implant and prevent this lateral micro movement. So you'll see it in like a Nobel, like the trilobes or the Brandemarks. You get a lot of lateral movement, crestal bone loss. This is very common knowledge. And the newer implants that we're working with have, much less of that. The other thing that we see here is that another happy accident was the notion of platform shifting. So usually in older implant systems, everything was uniform with the body, and it kind of followed that contour up. But what you notice is one time they put an implant in there and it was a little bit offset in, so the platform was shifted inwards. And what they noticed is that actually created a hermetic seal or like a bacterial barrier that helped with crestal bone again, as well as bacterial preventing bacterial infiltration. So all these different designs have culminated in very similar things that you'll see across many implants. But of course, the emergence also is very important. I kind of touched on it a little bit already, but the emergence profile itself is very important in preserving bone and keeping everything healthy by creating almost like a hermetic seal there for the implants. And then of course, where dental technicians live is the implant restorations. Everything underneath all that is all done clinically. This is where we really come in, and we have to make sure that fabricating restorations is done properly to make sure that we are adhering to those rules of preserving crestal bone, making sure that osseointegration is encouraged. So there's a number of things that have changed over the years. When I first started working with implants, it was all stock abutments or custom abutments that you would cement. We've overcome that because we've learned that dental cements themselves are kind of dangerous around that implant fixture. So mechanical stress, obviously, if you're improperly cementing it, the mouth environment is moist. It's very challenging. Trying to cement and isolate, sometimes what happens is maybe it sets up again a little bit too quickly, and there's excess cement that they can't see. Micro leakage, if it's not fully seated, will cause cements to deteriorate over time. And of course, some cements are corrosive to all the components. The newer cements are obviously engineered a lot better, but these are some things to consider. So of course, we've moved towards screw-retained restorations, right? So the ability to retrieve these things in the event of a failure. The aesthetics look much better. Now we have angled screw channels. All this is wonderful because it makes things much more predictable. And it's really an insurance policy, right? As technicians and clinicians, we always want to try to mitigate the amount of risk that we're setting ourselves up to. So kind of over-engineering these things, making them more predictable, and giving ourselves a layer of insurance is very important. And of course, that also allows for the top-down approach in designing restorations, right? I speak a lot about that just because it gives you better outcomes. You have surgical guides, you have implant planning, and now the ability to really predict all these things much earlier on in the process than just putting some implants there and trying to build something up. So of course, these are the 4 levels of implant restorations. And the next concept I always like to talk about is what I call the 3 Fs of implant restorations, so fit, form, and function. So factors affecting fit, of course, input records, the underlying bone underneath. So if you have soft tissue and bone and you have a very narrow emergence profile there, sometimes it can impinge on it and affect the fit. And then of course the luting agent as well. The luting agent acts, number one, to keep everything together, but there's also compensation in there, right? So that luting agent allows a degree of play. And this is what I'm going to talk a lot about today when we kind of move on to the topic of these screw-only systems versus titanium bases. So this play is very important because we're not perfect. Machining isn't perfect. The record capture is not perfect. Nothing's perfect. So that degree of play really, again, offers us a layer of insurance. So of course, passivity is another thing that I'm going to talk a little bit about. And passivity is the most important thing when working with full arches, right? So the gold standard, of course, is doing a Sheffield test, where essentially you take a full arch restoration, you put it on the model or on the patient, and you screw it in on one single fixture, let's say the most posterior one, and you look at the other side. If it lifts up, you have a passivity issue, right? It should seat fully passive every single time when you're working with these. And it's very critical to, number one, verify your records, make sure everything is done properly, and we've done all of our due diligence before proceeding, obviously, to any kind of metal framework or final restoration. So this is something that I see is actually often bypassed a lot, and also passivity in the mouth is very hard to visually or physically assess because, again, you have that tissue, you have that bone, you have things impinging, you have to apply pressure. So it's not going to be as passive a fit as you're looking at on a model in the lab. So all these things really need to be ensured beforehand. And of course, scan bodies are very important. ELOS is a company that's notorious for their scan bodies and working with a number of companies and providing kind of a universal standardized way of aligning between multiple different companies, right? So the scan bodies themselves and the design of the scan bodies and the engineering behind them also affect this, right? So the ability to scan these things in, how nicely they scan in, how long they last, the coatings on them, all affect the fit, right? So if you're working with a scan body that has an all-peak connection, right, those deform over time. And if you use them 100 times or you sterilize them, that affects the accuracy. So again, if we're trying to capture 6 implants cross-arch with a scanner, and that scan body is really old, or it's slightly deformed, or it's torqued down just a little bit more than the others, that's going to affect your vertical fit, right? And your passivity is going to be off. And there's really no way to verify these things digitally in the lab until we send a verification jig to the clinic. Factors affecting form. Of course, the implant placement itself is very important. If it's placed a little bit too high, a little bit too low, that affects the actual emergence profile and the aesthetics. If it's placed a little bit mesial to the adjacent teeth distal, if it's placed a little bit too buccally, a little bit too lingually, it just affects the form and the function. And that also affects the soft tissues around the emergence, the aesthetics. And we have to compensate for that with our design. So implant placement, emergence itself, and there's various different types of emergence profiles, right? So we have a flat emergence profile where we just want everything nice and straight. We have a concave where the emergence is a little bit curved inwards and it's curving towards the gingival portion. And this is very ideal in patients with like a thicker biotype, so the tissue is a little bit thicker. You have an emergence that's convex, so if we're using very large, like usually in the posterior region, the emergence is curved outwards to really create a large form there. And then of course you have like a scalloped emergence, especially for things like FP1s, right? So these are very difficult to do, but you typically find them in the aesthetic zone where it's very critical. I mentioned tissue biotypes already, but there are really just two. There's thin or thick biotypes, and really understanding this is very important for creating restorations and how you're going to design your emergence for that. Let's just take a picture. That one as well. All right, and then factors affecting the form as well. Again, implant placement, just a quick summary of everything. And all this is really related to the hygiene, you know, and preserving that emergence profile to get a really good relation to the crest of the ridge and all that other soft tissue. So function, of course, this is very important because this is where technicians are very responsible, right? So occlusion, if you have a compromised occlusal scheme, if the space is insufficient, we have to account for that. And understanding full arch principles and occlusal schemes is very important. The second thing affecting the function, of course, is the contacts, right? So if you have non-parallel or things that are leaning inwards towards each other, so on a single unit, let's say, most of the time you'll see an edentulous spans, that things kind of lean in towards each other and you have these kind of very unideal point contacts, right? And then ankylosis, right? So there's a lack of PDL. There's no proprioception for the patient. They have the implant, it's fused to their bone. It doesn't move, so if everybody just clenches their teeth, and just bites down just a little bit harder, you feel how your teeth just give a little bit, right? With implants, they don't have that same kind of feedback, right? So we typically are instructed to, if it's a single unit, to design these slightly under occlusion, just so that, you know, we account for that PDL, right? So these implants don't fail. Again, all on X cases, they need to be approached with a lot of care because all that force needs to be distributed evenly across the full arch so that we mitigate any kind of really hard forces or any excessive force on the implants and it's loaded properly. So a couple other things. Implants, like anterior teeth, they are single rooted, right? So they're very good at not lateral forces and not protrusive forces. They like to have everything loaded against their long axis. So they also, again, lack those periodontal ligaments. So we really need to design these things in a way that is most effective for the shape of the implant that we're working with. And then finally, we'll talk a little bit really quickly about complications. So mechanical complications, screw loosening does happen in all types of implant restorations, right? And screw loosening happens because these forces that are being transmitted through the restoration into the implant are not being dissipated properly, right? So let's say who has like a dining room chair that every once in a while, like the screws just feel loose and you got to go in there with the Allen key and tighten them up, right? That's because those forces are being transmitted through the leg and then the screw is able to just kind of back itself out. Right? So it's the very same concept, and it's happening inside the implant. So this is an indicator of some kind of excessive force that's not going or being dissipated where it's supposed to be. You also have material chipping, fracturing of the implant components themselves, and we'll talk about that as well. And then lack of passivity and all those excessive loads can, of course, ultimately lead to biological and mechanical complications. So obviously biological complications, let's say, for example, excess cement, which we used to see a lot more with cemented restorations. So you'd have peri-implant mucositis, peri-implantitis, and then ultimately implant loss, necessitating the removal of the implant itself. So prosthetic considerations that we need to take into account is, of course, in our planning stages, okay, what type of restoration are we doing, right? And this is a very common chart. You see this all over the place. Is it an FP1? Is it an FP2? An FP3? Are we going to go with an overdenture style? Does it need a flange? Does it not need a flange? And all these things are spoken about and discussed during the planning stages, right? So you know how much bone you need to remove or level off, or what type of fixtures and where they need to go. We need to make sure we're managing the vertical dimension of occlusion, making sure we have enough space, of course, midline, smile line, all the aesthetic considerations as well, managing transition lines, right? So if you're working with FP3s and very atrophic ridges, what you're going to see often is the ridges are kind of resorbed backwards. And if you don't have that lip support there, you're going to have almost like a transition line that it's like a balcony. One of my friends calls it a sandwich storage facility because you get to keep your sandwiches there and get a little bonus later. So often, if you don't have that kind of lip support, we might have to go with like an RP4, RP5 to get a little bit of a flange there, right? And patients don't like that, but it does give them like a fixed feeling. But that's ultimately between the clinician and the patient to discuss these different challenges, right? Again, occlusal schemes are very important as well. Understanding occlusion, flat plane occlusion. Who here is primarily crown and bridge? Okay, dentures? Okay, so myself, I'm a crown and bridge technician, so my formal training is, you learn to do one PFM, you do a second PFM, you do a 6-unit anterior EMAX, you get really kind of confident with yourself. I'm going to do a full arch, and it's just like the mentality of doing 16 or 14 crowns, and that's how crown and bridge technicians really tackle full arch. Whereas denture technicians are focused on, the setup, the occlusion, bilaterally balanced occlusion, lingualized or 0 degree, and what I find is implant restorations really need to be a combination of both kind of schools of thought because neither one, it really works in implant restorations because again, if you're working with a bilaterally balanced occlusion for dentures, you're doing that because you want to retain the denture in a way that it's not going to be dislodged when it's functioning. But because we're working with implants, everything is fixed in place, you don't need to have those same kind of working and balancing contacts. But at the same time, you don't want to have a crown and bridge mentality where everything is in MIP essentially, and you have these things knocking into each other constantly, and that's where you find chipping and all these complications with having everything too intercuspate. Freedom of movement and freedom in centric is really the concept for that there. So some prosthetic considerations. Okay, are we going direct to fixture? Are we doing custom abutments? Are we doing multi-unit components, right? And typically we want to do multi-unit components because of this little animation here. It's not going to play. Did it play already? So essentially, let me see if I can do that again here. Play. You guys see that little bit of movement back and forth? Okay, and that's that slop factor tolerance lateral movement that I was speaking about a little bit earlier. So again, this is the multi-unit abutment that's screwed into the implant itself. And this is a titanium base with a flat seat screw that allows for a little bit of lateral tolerance, right? And that lateral tolerance is very important because it allows that imperfection in our manufacturing and our data capture and whatever it may be along the process to be a little bit forgiving in things, right? Are we going to use locators if we're doing RP4s or RP5s? And then, of course, if there's not enough vertical dimension, do we need to support it with a bar? Do we need to support it with a framework? Is it acrylic, wrapping a bar? All these things, again, are considered during the planning stages. Materials as well, very important, right? When do we want to use PMMA? When is a full monolithic zirconia important? Are we going to wrap it with acrylic? Is it the new kind of B4D style with zirconia on top and then like a nice metal intaglio? This is a very hot topic, of course, and probably the reason why a lot of us are here today. Do we want it, again, locator retained or Novalock retained? What about hybrid print materials, 3D printed resins? I'll touch on that as well. So of course, the big thing is strength, durability, and biocompatibility of all these materials, right? So we have to consider all of these things when factoring in the restorations that we're fabricating. Also the techniques, I don't think anybody's casting bars anymore. I think machine bars are much, much better, but we used to have to cast these things. Milling is, of course, kind of the gold standard for manufacture. And then 3D printing is kind of growing a lot. I'm a little bit skeptical on 3D printing. I'm a huge 3D printing advocate. If you guys want to hear my thoughts on 3D printing in more detail, I'm doing another lecture a little bit later today about 3D printing. And then, of course, injection methods for conventional processing. So again, let's go back, because we kind of went through all those implant fundamentals, but let's go back to why this topic matters, right? So why does screw-only versus tie-base matter, right? Why do we need to rethink this whole process? Of course, we're talking about the reduction in costs, the machining limitations that I've kind of touched on already, and it is, of course, a more modern and well-marketed process. But of course, now that we kind of all are on the same page in terms of implant fundamentals, screw loosening, potential stress that's transmitted to the screws or excessively in other directions, and of course, not interfering with osseointegration and crestal bone loss and all that stuff. So this is one of the designs of a screw-only system, right? So you can see here, relative to that other image I showed you earlier where it had a titanium base with a screw with a flat seat, this one here has a conical design, right? And it's like that for a number of reasons. The first reason is that it is meant to wedge itself in here, right? To kind of self-center itself and wedge itself into the material so it holds the material there. The second thing, of course, is it's designed this way because of certain milling machines not having any flat componentry, right? So if you're not able to mill flat screw seats with, let's say, your Roland, it doesn't have a flat screw or a flat end mill. You have a ball only, right? There's no way to mill a sharp 90-degree angle with certain cheaper mills, chairside mills, anything like that. So this design here is designed to overcome machining limitations and make it kind of more accessible to the masses. But of course, that introduces some potential challenges. Like I said, no machining is perfect. You know, when's the last time you guys calibrated your mill? When's the last time that the person taking the scan calibrated their scanner, right? So this here, what this is showing is the heat map, depending on where that contact point of these two tapers, if it's a little bit lower, that stress point is going to be a little bit lower on that screw seat. If it's a little bit higher, it's going to be higher on the screw seat. And that really affects the way that those forces are transmitted through the implant as well as the screw. So if it's a little bit higher and they're laterally functioning on it, right, it's going to cause the screw to kind of wiggle itself back. And ultimately, it could also snap the screw. But also, these forces are being transmitted eccentrically through the multi-unit abutment all the way through the implant itself. So all of this is not ideal because we're transmitting these forces. That wedge is, especially if you're doing an immediate load, right, and you want those implants to osseointegrate over a period of, let's say, 4 months, any excessive movement on the lateral direction or even vertically is going to cause less osseointegration, right? It's not going to be as well integrated into the bone. So the definition of clinical passivity that's kind of generally accepted in literature is 100 microns of misfit within 1 degree of deviation cross arch. And digital workflows, they really try to account for this, right? So, but a lack of passivity really increases the risk of these stress fractures and then overloading the implants in excessive ways, right? So either you're loading one side of the arch much more than the other, or laterally, depending on whichever direction. A really great, one of my favorite presentations, Casper, one of my favorite presentations to this very day, Casper here, when we basically first met, he did a presentation about, and this was absolutely eye-opening to me. Take a picture of that QR code. And he really goes into detail about, excessive loads, forces, not passively cementing everything, all the protocols. And it's just something I really recommend to everybody to see if they're working with implants, just because it goes into such detail and it's presented in such a way better than I could ever explain it, in such a way that's very eye-opening for tolerances and passive fits, right? So I still recommend this to so many people all the time. But again, the role of titanium bases, right? We spoke about this already. Titanium bases, substructures like bars, they really ensure passivity and stability, right? So titanium bases are manufactured in facilities that have lathes that are much, much more robust than anything we have in dental labs or clinics. They have extremely tight tolerances. Casper, obviously you can comment on this. You guys go through a lot of regulatory oversight to make sure that everything is within tolerance. You go through all the regulatory to make sure that everything is adhering to these specifications, right?
Yeah, and demands, regulatory demands are constantly increasing.
Absolutely, yep.
And we're putting more and more resources into it.
Absolutely. Yeah. So these components are machined to such tight tolerances that when you have the implant itself and you have these titanium bases, they're going to be machined in such a way that it's going to be passive. It's going to have that lateral play for us, or that tolerance in it. And it reduces those transmission of forces into the implants, again, because we want to preserve the implants and the bone as much as possible. But the other really big thing here, is radiopacity, right? So as clinicians, whenever you guys are placing these into the mouth, how do you verify passivity, right? You take a radiograph, you look at it, and you see the metal interface of the titanium base, and you see the implant together, and it's all mated together very nicely. And that's how you visually inspect for passivity, right? Is that fair to say? Absolutely. The other thing, of course, is substructures, very hot topic, is B4D I-bar, right? So this is very, very cool tool because it prevents zirconia from fracturing, right? As technicians, we want to make sure that our products are robust, over-engineered in such a way that we CYA, cover your ass, right? And you want to make sure that everything is on your part is done very well. But counter to that, if you're over-engineering these things and you have a lack of passivity, right, where are those forces going? Titanium doesn't fracture, okay? If you have a lack of a passive record and you screw this in and the doctor torques everything in and all these forces are kind of held in tension cross arch, that titanium's never going to break. Those forces have to go somewhere. Where are they going to go? Into the implant, right? And you see this as well. So if you're torquing these things down, over-engineering is great to a point, but understanding that if you're over-engineering these things to the detriment of something that's significantly more expensive. Yes, redoing a full arch all on X is expensive. Redoing all of the records, yes, it takes up a lot of time, but having the clinician explant an implant that's fractured, that is significantly more expensive to the clinician and the patient, right? So we have to consider these things. I really enjoy, obviously, over-engineering things, tolerances, everything like that, but this is one big pitfall of the workflow of working with something like B4D I-bar. So, looking at precision in milling and some of the sources where errors are introduced, right? So scanners themselves, so the intraoral scanner that we work with, it's very common knowledge that the example I always kind of give is, let's say I want to have a point on the wall here, right? I'm going to mark a point on the wall here. Freehand, I'm going to walk all the way around the room, trace a line, and then I'm going to try and come back and meet that same point, right? What are the chances that freehand I'm going to be able to do that? So the same thing goes with any kind of intraoral scanner. So if you're scanning from one side of the arch, and the scanner's just askew a little bit, and it tracks across the arch form, and it comes all the way back across, and you see this during scanning even, where they will scan, and then it'll come back, and the two surfaces are just a little bit off. They have some assist technologies and AI technology inside that trying to interpolate the information in between, but at that point, that record isn't a passive record. So again, we have to verify and account for this, right? Tolerances in 3D printing and milling as well are huge, right? So when the last time you actually calibrated your mill, how tight tolerances those mills are. What are the components made out of? Some mills have plastic components in them for gears, some have more robust metal components. So really understanding why these robust mills are much more important in this machining. Aligning scans improperly, of course, very much similar to the scanner drift, but on the technician side in the CAD software. So of course, technologies like photogrammetry, using a desktop scanner. A desktop scanner is still probably the gold standard, only below, let's say, a Renishaw touch probe, right? But a desktop scanner is going to be passive because you don't have anything moving on the arch. You have a fixed point, and everything, when we scan these things in with scan bodies, it's very passive. So taking a verified record, pouring up a model from it, and then actually scanning it in with the desktop scanner is still kind of the gold standard for really getting digital records that we can work with. And then of course, quality control, taking these things, scanning them back in, overlaying them with heat maps to make sure that we're really within tolerance. And we've talked a little bit about this already, but again, that passivity, that slop factor left and right, they have a cement gap around the actual top of the tie base as well that allows for a little bit of play in cementation. ELOS, on the other hand, they do a little bit of a cool thing, and we'll cover that as well. But the engineering that they've put into this, and this is one thing I'm a really huge advocate of, is actually cementing tie bases intraorally, right? So one thing that a lot of people are doing nowadays is they're using screw-only systems, right? And they have these screws, and they're 3D printing these things. Anybody know off the top of their head how accurate a 3D printer is cross-arch, roughly? No? Okay. So typically you're going to find anywhere from 200 to 300 microns plus or minus cross-arch. And quick quiz, what was the definition of passivity cross-arch that I mentioned earlier? 100 microns cross-arch within 1 degree, right? So that's not passive at all. So if you're 3D printing a full arch, you're loading it immediately and it's 300 microns off, what do, right? And you're loading these implants excessively for 4 months while they're integrating. So the better way to do it actually is if you're going to be 3D printing, I'm a huge advocate of using these types of tie bases that have this conical shape that has a little bit more room for deviation and the ability to be picked up intraorally versus a straight tie base that has a much more difficult draw if these implant fixtures aren't perfectly parallel. So then what you do is you screw these titanium bases in the mouth, you design it over a titanium base library, and then that print, if it has 300 microns, and you put it on there, you have that tolerance, but you have a perfectly machined fit to the implant interface, and the cement around it when it's being picked up is really what's accounting for that. So you're mitigating that lack of passivity when using something like this. It is, of course, a little bit challenging for the clinician to do all this. There's plenty of moisture, isolation, and a lot of things to do, but this, in my opinion, is really the gold standard if you want to do a 3D printed workflow. And of course, using angled screws and being able to angle correct is very important as well. So again, ELOS as a company, they take everything that I've spoken about earlier into account in all the engineering that they do for their componentry, right? And I think it's just wonderful when you look at the level of engineering that goes into this. So of course, again, this one is a little bit different because they're trying to mimic the original shape of the screw. And it's a little bit different because they have very tight machine tolerances. This is completely different from what I was talking about earlier. They have these wedges because they are designed with the components in mind, whereas other competitors don't have the same kind of precision, essentially. So this is a fun one. I had Chris earlier, you spoke to me about this. How do we machine these things, right? So people who are working with these screw-only systems, typically zirconia has a shrinkage rate of 1.22 or 1.25, whatever it may be. So these patterns are much, 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 much larger. So I had a colleague of mine who reached out to me and he started working with these and he said, hey, you know what, I got the library for this thing, the doctor did the case, I gotta send it to him. It's direct to PMMA with the screws in it. And if you look very closely here, does that look well machined at all? No, it's very rough, right? And why is that, right? And I'll go through a couple more pictures here. This one here, he goes, oh, I don't know what's going on here. Like every time I try to machine it, it's just, like I can get the screw. This one, I adjusted it by hand and the screw sits in, but it's kind of tight. You can see from the top as well. Right, that doesn't look good. So he said, you know what, I'm going to adjust all these by hand. And if you remember that slide I showed you guys earlier, if the contact point is a little bit higher, a little bit lower, those forces, where are they going? Where are they dissipating, right? So if you're doing this by hand at this point, where the fit is going to be all over the place. A couple more pictures here. I'm going to show you some cross sections as well. So the problem with this is, number one, if we think about machining, right, the burr itself is a 1 millimeter burr, but it bottoms out because the shank actually comes in to this area and it bottoms out and it cannot reach this point all the way down. And the diameter across of this is like a 1.5, right? So the 1 millimeter burr, in theory, should fit in here. But if these designs are extremely high, and especially if it's an FP3 or anything like that, you're gonna have really, really, really long screw channels that these burrs are simply just not gonna be able to reach in there. So essentially it was milling from the bottom and milling from the top, and this dead zone in the middle here, where it starts to taper, has no way for it to reach. So same thing with zirconia. Obviously it's a little bit wider, so the burrs can go in a little bit deeper when it's in the green state. But again, when you're milling these things, and if the burr cannot reach in here, you're absolutely dead in the water when it comes to accuracy. So this is why I'm a little bit skeptical about these systems. I think they're definitely innovative, and the other thing that we see very often is, they have like thread lockers, or they have additional geometry in the screw to prevent the screws from loosening, right? But instead of, all you're doing is putting a Band-Aid over a problem, right? If you're locking these screws into the plastic and it's grinding or it's wedging itself in there, where are those forces going, right? And that's one of the big things that really disturbs me about it. Oop. So now if you look at the ELOS components themselves, right? They are designed in such a way that everything is machinable. It accounts for that 1 millimeter burr, right? It accounts for all of that. And also, they do have built-in, that video didn't play? Oh, that's weird. I thought that video would play. There was another video here, but anyways, if you look at this here, you can see that they still have cement gap built in. They have rounded edges to account for machining. But the other really cool thing is ELOS understands that we are human, right? We have some issues like when we're cementing these things. So they have all these guiding planes engineered in as well, right? So they're very subtle, but they're flat, right? And it helps us to make sure that when we're cementing these things, that it's perfectly passive to the way it was designed, while still accounting for some cement gap, for some inaccuracies. So again, some key takeaways here, and just some points hopefully that I can get across here. Screw-only systems, they're good, they have some merit to them, but they really should be used in kind of like a temporary or really with a lot of care, right? So if you are able to machine these things in such a way that you can account for all of those inaccuracies that I've spoken about. But otherwise, if your machining is not up to snuff, then they have a lot of tremendous biomechanical risks. Titanium substructures, right? So we spoke a little bit, B4D I-bar, I think is a wonderful tool when used in the right capacity. If, again, we're torquing all these things in a tensioned state, it's gonna lead to implant failure. And we wanna mitigate our risk there. Proper digital verification is really how we overcome all of this stuff, right? So using photogrammetry works. Photogrammetry is not a silver bullet, it's not perfect. It still has optical limitations. I've done hundreds of cases with them now, and there are limitations to all optical technologies. A physical verification jig is always going to be the gold standard, and the ability for you to digitize that in a predictable manner is really important. And then finally, the emerging materials themselves, right, are going to kind of reshape the debate, and talking about 3D printing and how that's going to make things obviously a lot more efficient. Teeth in a day as a concept is a very cool thing. But we really need to consider the limitations of the manufacturing processes and what those materials are doing and how they could potentially affect the implants in a negative manner. So with that, I want to say thank you, and I'll open the floor to questions as well. And we got a little bit of time for that. So thank you.